To kick off our afternoon, I'm really excited to introduce Armon Dadgar. Armon is the co-founder and co-CTO of HashiCorp, and he's here to talk to you about Nomad. So please give it up for Armon.
So today I wanted to spend a little bit of time talking about Nomad and how we can leverage it in next generation application architectures. So for those who aren't familiar, I think Seth sort of beat me to this. I'm one of the founders and CTO. And I think you've seen this one now a few times in terms of like how we think about the problem space and delineate the challenges. Today I'm just going to focus on Nomad and what we can really do in this space when we change sort of our perception of what the scheduler is and how it actually gets leveraged by our applications themselves. So when we talk about Nomad, it's been mentioned a few times that it is a cluster manager or an application scheduler, and it really is both of those things. But the groundwork I really want to set is sort of when we talk about a scheduler, what are we really talking about? Right? What makes a scheduler a scheduler? At its sort of core, at the most sort of philosophical level, if you will, the goal of a scheduler is to map a set of work onto a set of resources, right? Sort of vague, so let me ground this in something a little more concrete. An example of something we're probably familiar with or have heard about is a CPU scheduler. So the function of a CPU scheduler, and we are surrounded by these, we have them in almost any device, is to map sort of the virtual work of processes and threads onto the physical world of CPU cores, right? So your laptop maybe has 2 cores or 4 cores, but usually there might be hundreds or thousands of actual inputs, work, that we want scheduled on top of that, right? And so the challenge is, well, there's no static way to assign 2,000 threads onto only 4 cores. So instead, we need to take a more dynamic approach where we're scheduling that work as we go. And this really is the function of the CPU scheduler, right? The input to that system is the set of virtual work, and the resources underneath it are what it can leverage to achieve that. Now, over time, the scheduler is going to move things around. It's not going to be a static assignment of what's running where. This lets the CPU scheduler provide a higher quality of service and also create the kind of virtual illusion that everything is running at once, even though we don't actually have the hardware to allow that to take place. So CPU scheduler is really just one example of a scheduler in the wild. In reality, we're kind of surrounded by schedulers. We see them all over the place. CPU scheduler fills the function of mapping the virtual threads, the processes, onto the physical cores, but there's all sorts of other types of schedulers, right? This is just meant to be sort of a very small example of what's actually out there. If we really think about something like EC2 or OpenStack Nova, it's doing a similar sort of thing, but at a coarser scale, right? It's mapping a virtual machine, which is maybe 4 cores and 8 gigs of RAM, onto a set of hypervisors, which are physical machines, right? But it's this sort of dynamic mapping of work onto this sort of set of fixed resources under the hood. When we talk about something like Hadoop or the Spark scheduler, they're doing a similar thing. They're mapping sort of a query or a batch process onto a fixed cluster as well, potentially running multiple jobs at the same time, overlapping their execution, putting things in queues, but it's filling that mapping role. And so when we talk about a cluster scheduler, so something in the context of Nomad, what we're talking about is mapping applications onto servers. So it's within this context that we're going to talk about Nomad. And so the goal of schedulers, almost regardless of whether we're mapping cores onto CPUs or applications onto servers, is to really achieve 3 things, right? One is higher utilization of our resources. The other is to decouple the 2 things, so we don't want our work to be intimately connected with the underlying resource. And the last one is to achieve a better quality of service. And this sort of will vary depending on the application, right? So if we're talking about a desktop CPU scheduler, maybe we care about responsiveness. So if I'm clicking around, as a user, but my machine's really busy, I want the machine to feel responsive. That's not necessarily a concern for a cluster scheduler. It doesn't care about a user clicking around. It maybe cares about overall density or minimizing time in queue. So there's a number of approaches that we'll leverage to achieve each of these things. And I'll just touch on them sort of briefly. When we talk about optimizing for resource utilization, the sort of core bit of that is what's known as bin packing. And this is the algorithmic approach to sort of saying, I have a number of boxes that I'm trying to fill, whether they're sort of servers or cores or whatever it may be, and how do I sort of maximize the stuff I can use in that or conversely minimize the amount of wasted resource, the amount of resource I'm not using. And so bin packing is a well-known algorithmic approach to doing this, where you try and minimize that sort of unused space, and this leads to a higher resource utilization. The other approach is resource oversubscription. So where we're most sort of familiar with this is memory over allocation. So oftentimes machines will allocate more memory than they actually have available. And what we'll end up with is, if we actually try and use all of that memory, it'll swap to disk, right? So we've over-allocated memory on the machine overall, and we have sort of measures in place to make sure things don't sort of fail catastrophically. In the land of sort of cluster schedulers, you do the same sort of a thing, where you'll say, the applications have requested, 10 gigs of memory on a machine that only has 8 gigs. We'll provide that to them. We'll allow this oversubscription. And if that memory tries to actually get used, then you'll kick into sort of counter control measures to keep the machine from crashing. And the last one is job queuing. So how do we actually ensure there's a steady stream of work? Well, you just queue it up, right? You don't sort of fail when you run out of capacity. You put it in the queue, so as new room clears up, that work instantly starts executing. The next one is a decoupling of resources from the actual work that's being done, right? And the way this is done is really 3 primary techniques. One is abstraction. So we sort of hide some of the essential details of the underlying resource, and this gives us some amount of portability. The other is an API contract, right? So we have to provide some set of guarantees to the application, the consumer, so that they can reason about how is their work going to execute, how should they think about modeling their resource utilization. So this is sort of hand in hand with the abstraction. And the last one is packaging. We want our app to be packaged independently of the underlying system so that we don't have that coupling. So a great example of this is something like Docker, right? It's wholly independent of, is it a Red Hat system and it should be an RPM? Is it a Debian system and it's a Deb package, right? It's an independent, flexible packaging format. And the last one is better quality of service. So like I said, this means different things for different applications. For a big data scheduler, quality of service may simply be, optimizing, the wait time in queue. So first in to first out, I want to optimize that. For a desktop type CPU, you probably care about things like real-time scheduling. And in sort of a more general case cluster manager, you care about some mix of things, right? You care about things like priorities. So high priority work should get access to resources before low priority work. You care about resource isolation. So if I've asked for, 8 gigs of memory and, I should actually be able to use that 8 gigs, some other app shouldn't be able to show up and take my resources away. And the last one is preemption, which is if I have a whole bunch of low priority work that's consuming my whole cluster and high priority work shows up, we should be able to evict the low priority stuff to make space to run high priority stuff. And together, these 3 sort of properties give us a higher quality of service to our applications. And so we talk about cluster schedulers. They're sort of coming into vogue last few years, particularly led with things like Docker giving us that flexible agnostic packaging. But these are techniques that have been around for quite some time, right? Google's relatively famous for running their Borg scheduler since the early 2000s. Amazon, if we think about EC2 as basically a giant scheduler, has been doing it since 2006. And big folks like Netflix and Twitter talk about how they've scaled their infrastructure up over the last decade using these approaches as well. So hopefully that provides a little bit of context in terms of when we talk about cluster managers and schedulers, what we're really talking about. It's how do we maximize our resource utilization? How do we get that decoupling? How do we get that quality of service? And our scheduler is Nomad. So I want to spend a little bit of time unpacking Nomad. Within the realm of being a cluster scheduler, there's sort of a number of goals we had for it. One was really thinking about sort of like what are the 2 primary users of something like Nomad, right? On one side, we have developers who are running applications, deploying new versions, scaling up and down, doing rollbacks. And so how do we make their life easy? How do we make deploying a service, managing a service, that sort of full life cycle as simple as possible? On the other side, we have folks that have to stand up and manage the cluster. So how do we make it operationally simple to deploy, scale, manage, do all of the operational bits? And then in doing so, in doing both of those 2 things, how do we ensure the system is built to scale so that you don't hit these sort of elbows in the scaling where you have to say, oh, great, I have to re-architect my whole application now because I've hit the limits of the scheduler, right? A system like this lives at the heart of your application, and it can be very uncomfortable to hit its sort of scaling limitation. And so in doing so, we can provide this API that enables next generation application patterns, right? Because we're confident in the ability of the system to scale and support at sort of any scale. Now let's sort of get into what that looks like. So for those who have never seen a Nomad job file, this is what they look like. Hopefully, non-threatening. They're meant to be human readable, human writable. These are what developers are actually working with to specify what their job looks like, their constraints, do the rollouts of new versions. So this ends up being sort of the heart of what a developer works with, is the declarative job definition. And so this is a very simple job. It's fully valid. It will run Redis using Docker. And here it's just going to run count one of it, basically, in the US East data center. The goal of the job file itself is very similar to sort of the philosophy behind Terraform. It's to be very declarative. We don't want to tell Nomad how to do anything. We just want to tell it, here's exactly what I want you to run. 1 Redis, 10 Redises, 1,000 Redises. You figure it out, Nomad. And so that job file really is totally devoid of any imperative detail as to what to do, where to do it. That is all left to Nomad. That is part of that abstractional API contract, is we've abstracted the developer from that. The developer doesn't have to know where, doesn't have to be aware of sort of the how something gets run. They just specify, hey, as part of my API contract, I want 1 or 5 Redis servers. And so what this is really doing is getting at that abstraction. It's letting us abstract the underlying machine and the work that's being done. And so we get this natural decoupling. In doing so, we really want to make sure we can support sort of the broadest range of applications that you might need to run inside of your organization, right? There's not one class of application. There's not one type of thing you want to run. So when we really talk about workload flexibility with a system like Nomad, we mean it in a very broad sense, right? On one side, there's things like operating system flexibility. So you have some set of Windows apps. You have some set of Linux apps. How do you run those in a unified way on one cluster? So Nomad has no issue with 20% of your fleet being Linux and 80% being Windows. That's totally fine. The types of workloads you want to run themselves tend to be varied. Probably the most common class we talk about is sort of our long-lived microservice applications, so web servers, API servers, things like that. Those are, of course, a first-class concern. The next largest class is really short-lived batch, right? So either a monthly billing run or a big data job or some sort of data transform. It's something that's going to run to completion and exit. It'll give up the resource. It doesn't need it perpetually. Sort of as a subset of that category is the cron workloads. So things like a billing run, for example. Maybe we do that on a weekly basis or a monthly basis. How do we actually let Nomad know, hey, here's the definition of my job, run this every month, this is the amount of resource it needs, and now we have a highly available cron. The last kind of workload is system agents. So these are things where we want to run it everywhere in the fleet. So a Datadog agent or a logging agent or telemetry, things like that, where we want it fleet-wide. So all of these workloads are considered first class to Nomad. And lastly is drivers, which as we touched on, sort of to get that decoupling of work and resource, we need to have these independent packaging constructs, right? We need to sort of free the application from being OS specific. And so this can come in many shapes, right? One way of doing this is virtualizing. One way is containerizing with things like Docker, Rocket, LXC. Those are all natively supported. The more traditional approach is virtualization. So if you have a VMDK or an ISO, you can feed that into something like QEMU or KVM and run virtual workloads on Nomad. And then as you get into things like static binaries or sort of fat jars or DLLs for C#, you can also provide those to Nomad, and it will wrap it with OS primitive containerization, chi roots and C groups, sort of everything Docker and Rocket use under the hood, sort of implicitly do that on behalf of your application. And so the goal of really all of this is to say, okay, if we have these declarative jobs, how do we really enable this infrastructure as code approach, moving up the stack from Terraform, which is looking at it from sort of storage compute network level, up the stack a little bit to the service application level, right? And part of that is saying, what do these applications need? They need to be able to integrate with systems like Console, to register their service, to do health checking, to discover their upstreams. They need to integrate with things like Vault, to be able to get database credentials, TLS certificates, secure key value storage. Jeff went into a lot more detail than I will. And this really highlights Nomad's approach to the problem, which is to say, how do we compose together these independent pieces to solving this broader problem, as opposed to trying to make Nomad sort of an end-to-end platform. So Nomad very much focuses on the cluster management and scheduling aspect and pulls in these other systems or allows you to integrate to sort of solve the full spectrum. The ultimate goal, though, really tends to be how do we empower our developers by decoupling the operations roles, right? How do we let our operators do the cluster management, do what they want to do without constantly being pulled in by developers, and how do we empower the developers to self-service? So when we then talk about the operators, they have a big role to play with Nomad as well, right? They're actually providing this as a service. So how do we make this as simple as possible for them? Where this really starts for us is making it a single binary with no external dependency. So Nomad binary can run as a client, can run as a server. There's no external data storage like Zookeeper or Console. It's fully self-contained. Next, we started by saying, can we build on the other systems we know and have learned about? And so for us, this really started with two different systems. One is Surf, which we don't talk about a lot, but is sort of our gossip system that lives in both Console and Nomad. And the other one is Console, right, which is really our consensus-based service discovery tool. And so each one of these systems has taught us different things, right? So Surf is a totally peer-to-peer gossip-based system for cluster management. And so what that means is it really gives us three different things. One is membership. Who is in my cluster? What's their IP? What data center are they in? One is failure detection. So great, I know these 500 nodes are in my cluster. Which of them is alive at the current moment? And an event system. How can I efficiently broadcast an update to all 500 members of the cluster in a reliable way? And so Surf really taught us a lot of these core distributed systems bits in terms of how you put together a large-scale system. And we've learned a lot from that, right? In practice, we have users that have single data centers running over 10,000 nodes of Surf, powering incredibly sensitive use cases. And so what this let us do is really simplify the clustering story and simplify the federation for users of Nomad. They sort of get this out of the box with one command, similar with Console. Console, on the other hand, taught us a whole lot about sort of building a higher level multi-data center service, right? So it provides service discovery, configuration, coordination, a whole set of features. And its architecture is very different. Where Surf was totally and wholly peer-to-peer, Console has a centralized server architecture. So it has a set of servers and a distributed set of clients. And what this really taught us about is how do you architect for multiple data centers out of the box? How do we leverage RAF consensus to build strongly consistent systems? And how do we do this in a large-scale production-hardened way, right? There's a lot of sort of difficult problems to solve there, but we have individual users of Console spanning over 100,000 machines, right? So we've learned a lot in terms of what it takes to make this work at scale. And so in bringing all of that together with Nomad, it started with the single binary. We didn't want to have external dependencies. High availability had to be there out of the box. And multi-DC and multi-region support shipped with 0.1, because these were all very important to us. The next aspect of this is how do we build it for scale? So great, it's operationally simple. It should be enjoyable and easy for developers to use, but it's not helpful if you have to totally re-architect your app when you hit 50 nodes or 500 nodes, right? We want it to be able to scale with you. So where we started with Nomad was really saying, what can we learn from Surf? What can we learn from Console? And pull in both sort of mature libraries as well as proven design patterns, right? Why reinvent the wheel? What we didn't have in sort of building that was any scheduling logic, right? Like neither Surf nor Console do any scheduling. And so this was a new area for us. And so what we turned to was research and said, great, what's out there? What is the state of the art in terms of doing scheduling at scale? And really what we looked at was really two major sort of camps of work. One was out of Google in terms of what they've learned over the last decade and a half with Borg and Omega, as well as AmpLab in terms of what they've learned from doing sort of the more big data scheduling around Mesos and Sparrow. And so these four papers were really the big inspiration as to how we actually build Nomad. In practice, the sort of architecture ends up looking very similar to Console with a twist. So for those who have seen sort of the Console equivalent diagram, you have the central set of servers that are electing a leader among themselves, doing replication of data and forwarding of requests. And then you have clients, and what's different about Nomad is the clients can now span multiple data centers. So unlike Console, where you have one set of servers per data center, Nomad has one set of servers per region, which might be a single data center, it might be a dozen data centers, it might be 1,000 data centers. And so we have these clients that live in totally different data centers. As we compose this into a multi-region architecture, it looks very similar to what Console Federation looks like with multiple data centers. So each of the regions has their set of servers. They loosely federate together over WAN using sort of Surf and Gossip as the backbone. And together they can form a global cluster. So you can forward a request to sort of any server for any region, and it will route correctly to kind of get to the correct server to process it. So as we started thinking then about the scheduling algorithm of, okay, great, this is what it's going to look like from a sort of an architectural standpoint, here's sort of the design goals, the sort of box we drew for ourselves was to say, okay, how do we make sure the system can tolerate hundreds of unique regions with tens of thousands of clients per region and thousands of jobs running on top of that, right? So we sort of set the box there and said, how do we step backward from that goal into what the architecture has to look like? And where we landed was really driving a lot of this from Google Omega's design, right? Google Omega, what's unique about it is it's optimistic in its concurrency. And what this really means is if you submit 50 jobs at one time to the system, it will not try and schedule them sequentially, job 1, job 2, job 3. It'll try all 50 in parallel, right? And so with Nomad, as you add more servers to it, as you add more CPU cores, it will just do more work in parallel. And this was really important to hit some of those design targets we wanted, particularly if you're looking at beyond service workloads to batch, where you can get these very high rates of concurrency, because it's not a developer issuing a scale up or scale down, it's automated, right? It's applications saying, hey, I need to spin up 100,000 machines, and doing it in a programmatic way. And lastly, the pluggable architecture of Omega meant that it was possible for us to fit these different types of workloads, whether service or batch or periodic or system scheduler, we could sort of plug in schedulers to meet different needs. And so what we wanted to do was say, great, well, these were the design goals. This is what drove our architecture. You know, let's put our money where our mouth is. Does the system actually do what we promised it should do? And so this is the million container challenge that we sort of put together for ourselves, right? Loosely based on sort of the C10K of the early 2000s, was to say, can it actually just run 1 million containers? And so what we did was launch 1,000 jobs, each with 1,000 tasks, a task just being, you know, an app to run, in this case Redis, for a total of 1 million containers running Redis. And we launched all of this on top of GCP with 5,000 hosts. And what we saw was Nomad does what it promises, right? And this is sort of what this graph is showing you is sort of 3 different lines. The topmost line is Nomad actually picking where to run something, so doing the initial scheduling and placement. The second line shows the sort of time lag to notifying the client that, by the way, you should be running Redis. And the third line shows the client actually acknowledging and sort of signaling that Redis is now running, right? So there's sort of a necessary trailing edge of schedule first, notify the client, and then it finishes running. And you can see that basically there's a linear line from 0 to 1 million scheduled instances in under 5 minutes. And then slightly after that, in under 6 minutes, all million instances of Redis are now running. So I think we can sort of confidently say we've run the world's largest Redis cluster. You know, on one hand, the instant reaction to this from a lot of folks was, why would you ever need that? Why would you ever need something as obscene as 1 million containers running, right? Like no one has that workload, right? And this, to us, instantly sort of triggered that reaction of like, 640 KB should be enough for anyone. Like, what are you doing that you need more than this much memory? And what perfectly highlighted it for us was literally days after we published our C1M challenge, we got a note from a group, from the Citadel group. For those who are unfamiliar, they're the world's 2nd largest hedge fund. I think they have like $180 billion under management. And they came out and said, that's really cute. We like your C1M. We're curious if we can do a workload 40 times larger than that. And we're like, well, we don't know. We thought this was sort of the obscene scale that, okay, once it can do this, no one's ever going to come to us and be like, will it do X? And we were wrong. And so they came to us and said, great, we want to sort of battle test it at this next scale. And what they did was basically for 5 hours across 18,000 cores, continuously schedule work to just see how far they can push it. And they were able to sustain 2,200 containers a second at that scale. And so where we thought we were sort of pushing the limits, we didn't even realize that we're sort of one step behind even what's happening in industry. And so this sort of brings us to sort of what I wanted to talk about, which is what are those next generation patterns that you can start to actually enable when you have systems that can do this, right? When you have more than 640 kilobytes of memory, what can you actually do with a computer? And so where I think this starts, is what I sort of refer to as the service-oriented architecture spectrum. I think when we talk about services these days, we hear microservice, we hear monolith, we hear sort of function as a service. And to me, these are all just sort of points on a continuum, right? On one extreme end of the spectrum is one application, 10 million lines of code. On the other extreme end of the application is 1 million applications, each with 10 lines of code, right? And so there's a fundamental complexity of if you're, an app that's, running a Fortune 500 bank, you're going to have the 10 million lines. You just got to pick where they live, right? And you can slice it however you want, but you're never going to boil it down to 50 lines. And so there's this sort of utility curve on top of this of, there's certain pain points on the extremes that you start facing, and somewhere in the middle tends to be healthy. And the reason for this is there's two different trade-offs that you have to make. On one side, monoliths have this enormous application complexity, right? Each of the subsystems interact with each other in a complex way. You have these huge class hierarchies. It's hard to really understand what's going on. And changing something on one side weirdly breaks the other side of the application. And so you have this high level of inherent app complexity. On the other end of the spectrum, you have the million microservices that have a very high level of operational complexity. Now your operations really has to be very sophisticated in how you're dealing with this volume of things, right? The more sort of scale you inherit, the more things just break, right? There's just more moving gears. And so what lets us escape this on sort of both sides is abstraction. Abstraction allows us to sort of hide some of the details, hide some of the complexity, and sort of reach higher up on the scale, right? It lets us build bigger applications that can do more interesting things by sort of abstracting the lower level details. And so this sort of analogy that we see is what allowed these monoliths to achieve those huge code bases was frameworks, right? There's frameworks that sort of decompose them and said, great, you're going to have a separation of data management, of controllers, of rendering, of these different subsystems that sort of shard out their work, and they will compose together into a larger application. So the framework gives us that skeletal structure that lets us layer on the functionality. Schedulers are sort of the same thing, but for services. They give us that framework to say, great, here you're going to add an app that does an image resizing. Here we're going to add an app that does a video transcoding. We're going to sort of compose all of these individual services together into a larger application. And we're going to retain our sanity by using schedulers to abstract some of the underlying details of this. And so the key really is, can we abstract enough detail, not all of it, right? Because we still need to think about, okay, our app is running on hardware, and there are certain implications of things we should and shouldn't do and performance trade-offs. But can we abstract enough that we can really focus on service composition as opposed to things like deployment and provisioning and sort of capacity optimization? And when we start doing this, I think the first thing we start running into, the first pattern, is a sidecar pattern, right? And so this is sort of it's been emerging for a few years. Netflix has been pretty vocal about some of the work they do. And the idea here is that you run an application alongside the main process. So your main API server offloads some of its concerns to these sort of side processes, right? And this gets represented in different schedulers in different ways. So Nomad has an abstraction it calls a task group. It is a group of tasks, as you might expect. Borg refers to this as an alloc. Kubernetes refers to this as a pod. But what we're really all talking about is it's a collection of apps. One of them is probably sort of the main app or the leader app, and the other ones are co-process. And the kind of things you start seeing is different applications will start offloading different chunks of their functionality, right? Instead of trying to natively build in rich logging libraries, we start saying, actually, let's just build a common logging sidecar that doesn't really care what the programming language is or the framework is, and run it alongside the app. So now we don't need the Java logging library and the Go logging library and so on and so forth. You just build one in any language and compose it at an app level. The other, you can start saying other things like routing proxies. In practice, there's a whole host of interesting sidecars that we're seeing emerging, right? Some of these are used to drive things like configuration. So maybe we don't want our app to be aware of our custom configuration store or CMDB or console even. And so we'll abstract things like console with console template. You might abstract sort of your observability stack. So things like logging and telemetry, sort of hide those behind sidecars that are aware of the APIs. In fact, Datadog ships exactly like this. They give you a Datadog agent, basically, that is a sidecar that runs on every machine. And then you get into some of the more sort of sophisticated stuff around load balancing and server meshes, which starts to sort of get more intimately involved with the execution of the app. Right? Some things more traditional load balancing approach, some of them now looking at sort of layer 7, can you intercept on a per request basis as opposed to a per connection basis, but keep this outside of the application. So what's nice about the sidecar approaches, oftentimes they don't require us changing our app. It's sort of transparent that we're doing this, right? It's sort of just a configuration detail of, instead of reaching out over the network, just talk to localhost and your logging sort of endpoint is there. And so this is nice, but it doesn't necessarily enable us to do more dynamic things. It lets us sort of break down some of the way we're composing our functionality within one machine or one application, But it doesn't let us get richer than that, more dynamic than that. And the reason is we're sort of bounded by the abstraction of a process, right? There's nothing richer there to be like, I want to launch something over the network. And so this is where API awareness of schedulers comes in and sort of starts changing this. Because now if we can talk to the scheduler, if we can leverage its API in a dynamic way, then we can start doing richer, more interesting things with it. And so these are some of the ones I want to touch on briefly. So the first one is sort of the traditional queue example, right? And we see this all the time. It's sort of a publisher-consumer paradigm, where on one side we have a set of producers, web servers, API servers. They're emitting events like user signed up or user logged in, whatever. And maybe we're doing things like sending them an email or 2FA code or something like that, and it's running in the background. So there's a set of consumers that digest those events and process them. And once they're done, they throw it away. The event's gone. And so in some sense, what those workers are doing is batch work, right? It's an activity that runs to completion and then it's over, right? It's sort of ephemeral in nature. The challenge in the traditional model is we have to provision these workers in advance, right? Like the queue doesn't know how to start workers. It's just a queue. And so if there's no workers running there, no one will dequeue and actually run anything. So then when we start provisioning, we say, well, we want more than one instance because what if it goes down, right? We don't want the messages now to be stuck in the queue. No one consumes them, and work just piles up. And so typically what we do is provision way more than we need to, right? Either because we needed a very low rate, and now we have at least 2 for HA, or we need actually 5, but we're running 8, right? There's this sort of over-provisioning that leads to idle and underutilized resource. And so this is where Nomad Dispatch comes in, and Mitchell talked about it a little bit this morning. The idea being, can we actually just start the consumer on demand? So instead of having these consumers always sitting there, always idle, acting like an online service even though they're doing batch work, can we just treat it like batch work, right? So when an event actually comes in, launch the consumer, process it to sort of completion, and then exit, return the resources to the cluster. So we get the same queue abstraction. Our publisher is still shielded from the detail. They don't care about how the event is being published. They just want a guarantee that it does at some point get published. And Nomad can now act like the queue for us, right? If we submit more work than there's actual capacity in the whole cluster, Nomad will just queue it. It does this with batch work. It does it with service work. So it's not really different. It still wants to provide you that promise that the work will eventually get done. But now we avoid underutilization because we don't have to launch n+1 instances for availability. We don't have to launch them in advance. When the work shows up, great. If the machine running that worker dies, Nomad will reschedule it. We don't need to have sort of an n+1 story. If it fails, great. Let's deal with it at that time instead of paying the cost continuously. So what this looks like is actually a pretty small modification to how we define and use jobs. Here I've taken a normal job and basically added the required delta to make it a parameterized dispatch job. The moment we add the parameterized block, Nomad now says, great, this thing needs some parameters, so it is now a dispatch job as opposed to a job you want it to specifically run that moment. And here we're just saying we need an input every time this job is called, and anytime this job is invoked, start a Docker container with the myWorker image and feed through the input file to it. And so this could do, it could send an email, it could transcode a file, it could resize, an avatar, it could do whatever, right? It's a function as a service in some sense. And so from a workflow perspective, what this looks like is the owner of that service writes the service, writes the Nomad file, and registers it and says, here's my dispatch job called, whatever, my job. And now the web server shows up and says, please invoke my job, here's its inputs. And at that point, Nomad takes care of launching the consumer and scheduling the work to be done. And as we dispatch more and more things, there'll just be more and more workers running it, right? So we'll use the appropriate amount of capacity. So this starts to look a lot like function as a service or sort of an AWS Lambda model. The difference is really how small is our granularity, right? And so if we're doing relatively low volume stuff where latency isn't of critical concern, Nomad Dispatch is well suited. As we get into very high volume, latency sensitive, the setup overhead becomes prohibitive, right? It's sort of like, do you launch a web server for every single request, or do you sort of amortize that launch cost by launching and then letting it service many requests over its lifetime? Similar sort of a concern here. If it's a batch processing thing that only takes a few milliseconds, the overhead of actually launching it might be 2 orders of magnitude more than the actual work it's doing. And so how do we actually solve these sort of fast serverless type sort of patterns as these are emerging? Well, there's a few things we have to do. One is actually do more than one piece of work per execution, so process multiple events. We want to still dynamically scale our workers to avoid that over-provisioning, and we want some level of queuing so that if there's a burst of messages, we don't just drop them on the floor. And so what this can look like with a system like Nomad is still very similar. We still register it as a dispatch job, register it against our service, but now we add this intermediate controller. And the controller has a few functions. One of them is to receive the actual event. So now the web server fires it to the controller instead of directly to the server. And now the controller can choose, do I have enough capacity or do I need to dispatch capacity, right? So this gets to that dynamic scaling question. So in the case where we get an event and there's no worker running, that's a good opportunity to go ahead and schedule the first worker. And so this worker gets started and it pulls that job out of the controller, which is queuing it to prevent us from sort of dropping messages when there's no capacity. As the message queue grows, it's getting deeper because we sort of exhaust the ability for one worker to keep up with the events. Then the controller can make the decision to continue to scale up. So as these queues grow, we make this adaptive and just dispatch more instances of the worker as we need them to sort of accommodate that sort of growing queue, drain the queue back down, and now we sort of right-size the workers. Another logical sort of a fit for this sort of dynamic consumption of resources is big data processing, right? These are applications that tend to be very large scale of consumption of compute. They have complex graphs, so MapReduce is maybe the simplest example, but usually you have sort of a chain of different jobs that are processing and feeding into sort of future jobs. And so at each of these phases, there's sort of different sort of widths to the pipeline. Your map phase might be very wide, your reduce phase very narrow, it fans into another map phase that's very wide, so on and so forth. And so what we'd like to be able to do is programmatically set up and tear down the workers to right-size each phase. So we're not just sort of using the maximum amount of compute and just having it be idle most of the time. And so one direction we're taking this with native Spark integration, which Mitchell touched on. And so what this looks like is totally native to the user. The user submits their job just like normal to Spark. Spark then goes and talks to Nomad to figure out, OK, I need 50 executors or 500 executors, and Nomad will dynamically provide those to Spark and scale them up and down as appropriate for each job and phase. And what we've seen in practice is the value of merging these things, right? And this is particularly something that Google spent a lot of time sort of studying and looking at is why not have separate data clusters from separate services? It's a very different workload pattern, and so why not sort of deal with them as a separate issue entirely? And what they found in analyzing their different cells, their different sort of data centers, was that the overhead in doing that would vary from, you can sort of see the CDF on the right, from 0% in very rare cases all the way up to a 60% overhead. So they need 50 to 60% additional hardware footprint if they did the segregation. And so this adds up to being a pretty large sum of hardware for most users. Now, of course, Google may not be representative of all use cases, but you sort of get an idea, right? That across these different workloads, there's a spectrum of overhead, but it's almost always more than zero. And so what becomes interesting as we start talking about the scheduler APIs and doing this dynamic behavior is this API starts to blur the line between what an application is and what the underlying infrastructure is, right? So when we think about something like Spark, yes, it's a user-facing application, but it's intimately connected to the infrastructure and how it consumes it, right? So it starts blurring that capability. As we talk about things like serverless controllers or dispatch, right, there's a fine line between is this an app concern, is this an infrastructure concern, and I think you can enable richer functionality by blurring that line. So our goal was to really look at this and say, how do we enable that dynamic behavior by providing the right contract, the right API, but still sort of providing all the other promises of Nomad, right? Which is higher resource utilization, better quality of service, right? A decoupling of concerns. How do you still get all of that while still leveraging it in this sort of very visible way to the application? So that sort of sums it up. What Nomad really is looking at is how do we be a great cluster scheduler? So just focusing on that task of mapping applications onto underlying servers, looking at our developer audience and saying how do we make it easy and pleasant for them to use and flexible enough to handle all their applications, making our operators' life simple by really being concerned about how the architecture is going to make them deal with the system. And then building for scale, particularly to implement this sort of next generation pattern, right? If we give more than sort of 640 kilobytes, what cool things can you actually build on top of it? And hopefully it sort of seeded some ideas for the kinds of things we're starting to see and starting to talk about. Thank you guys so much.